All right, so we'll start with the session, Accelerating ML Inferencing with WebAssembly and Spin 2.0. So, yeah, my name is Saiyam Pathak, and I'm a field CTO at Civo. Civo is fixing the broken cloud. And with me, I have Radu, who is CTO at Fermion. So starting off with very simple stuff and the basics, and then moving on to how we can actually deploy machine learning inferencing application locally, talk to GPU in Kubernetes, all the three. And yes, we'll try to do everything live. Um, so knowingly, unknowingly, and if you like, you do not like, you are using machine learning in like everywhere. So the songs that you listen on Spotify, you get recommendation for the playlist. Airbnb, you are staying, you get the recommendation for the next set of apartments that the others have booked the same one, and then you are shown with respect to the prices and stuff. You go shopping, you eat food, all those recommendations. So we are all the end users already before the hype. We are the end users of machine learning in the apps. Now, the Gen AI movement obviously has been because of ChatGPT. It obviously blew up the internet and a massive user base of how we can actually interact with a system that understands us and gives us the input with respect to the conversation that we want to make, and keeping the context alive and giving the relevant information, although it's still not very up to date with the latest stuff, but whatever till date it is being trained on, it gives you the appropriate answers. So think of it like as the big brain of the internet, like a small chunk of the internet put in the brain, and you are actually asking that brain the question and getting the answer out of it. So that's what you do. You have a chat interface that's simple. You just put your message in with the context that you want, and it's able to understand. You can do spelling mistakes, it's still able to understand. You can just put random stuff and then give you a question, it's still able to understand. So it acts like a brain and gives you the answer, and it creates a lot of content for you. Before getting more into the inferencing, so there is AI and there is machine learning. In AI, it's, you can think of it as like very, very simple terms of creating the system, intelligent system agents that can reason, learn, and show the human-like capabilities. On the other hand, machine learning is trains the model from input, and then the trained model can do the prediction based on the trained data. And two main categories are supervised and unsupervised learning. And it's pretty simple. Like in supervised, you can actually label the data, you can add some metadata to it to make it more structured, and then it can learn from the past examples and then predict based on those examples. And then you have the unsupervised data, which is untagged. And here, what we try to do is it's the clustering of the data that you try to do, because there's no exact tagging that you can add for the data. So that is categorized as unsupervised. Maybe it's more clear from the examples. So we all know about the spam emails we get every now and then. So you can see when you get an email in your box, some of the emails automatically goes into the spam, your spam folder. So that is basically the train on the labeled data set and tag whether that, so the training is tagging whether this particular email is spam or not based on a lot of data, like the words, the email addresses that are being used. So that's how the training is done. And in the end, the model is able to predict whether the new email that came in, now the new email was not in the training data set, but based on the training data set, it was able to predict whether this particular new email is a spam or not spam. On the other hand is the unsupervised, where, for example, what people buy and recommend based on that. So it's a customer recommendation. So let's say you have a group of customers. So here the group customers together based on purchase type, frequency, spend. So you have a customer who bought something, how many times in the week they are buying, how much is their spend when they are on a particular website or they are in the store. Based on that, you can cluster some of the customers together and then recommend each other their set of purchases, or do targeted marketing campaigns on specific set of users who buys this particular products in this particular range. So you can target a specific marketing campaign. So model should be able to predict, recommend products, enhance the experience of the customers. So that's the unsupervised data. Again, we have the input is given to the model, the output, it is compared with the trained data, and then it checks the output against the predicted output, like what it should be. If it's too far from where the answer should be, then it goes to the error, and then it goes to the, we have to like update the model till we get very close to the precision. Next up is deep learning, which is a subset of machine learning. It uses neural networks with many layers for complex patterns. You think of it as, again, as a human brain, which has many data points on it. They are interconnected and making like, and there's a lot of layers of this as well that makes it handle the complex predictions, and works on both labeled and unlabeled data. So that's why it is like able to predict more. You have this is where the Gen AI would fit in. And generative AI is more of creation of the content, and you might have seen in all the stuff that you're doing. For example, you are generating text, you are generating an image from the prompt, you are also generating videos. Like Sora is still in beta, but you have seen the demos how it looks like, and also Runway ML. So you have the set where you have text, image, video, graphics, all these. Then you have the models, like you have LLMs for image, you have diffusion for videos, you have diffusion, and then the application. So for the text, LLM, and then you have Chat GPT as the application side of it. So you can be in all the domains. You can be at the foundational level where you are the machine learning engineer doing all that stuff. You can be at the model level, or you can be at the application level developing the applications. So this is a small context of where the machine learning ecosystem is. Now coming to the AI inferencing. So AI inferencing is the phase where a pre-trained machine learning model applies its acquired knowledge to analyze and draw conclusion from the fresh, unseen data. So you can have different tooling for it. For example, you can have TensorFlow, PyTorch, you can create an inference, and then it's basically you are trying to call the, for example, let me give you an example. Let's say you have created an inference for generating the image. So you have a model which is there, and you want to use that model. So any input that comes, it goes to that model and gives you the output from that particular pre-trained model. So for example, speech recognition, image detection, autonomous vehicles, these, I mean, there are a lot more use cases, but some of the use cases over here. So this is the AI inferencing. Now coming to why we are here. WebAssembly and AI inferencing, why it is a hot topic, and Second State is doing a lot of things. Fermion is doing a lot of things in the AI inferencing space with WebAssembly. So yes, when we talk about Python, it is very good. Like obviously, it is only being used for, mainly being used for training and inferencing, all the stuff. For training, it's fine, but when it comes to the inferencing, there are certain things that it has some challenges, and with the technologies and tools that we have today, we can actually overcome these challenges, and WebAssembly is one such technology. So for example, efficiency is one. So how do you get on-demand GPUs, and you only use that you can only use for the inference? With WebAssembly, it makes the resource usage efficient, and you actually consume, since it's a smaller binary size, and by now it's a second day after coffee break, you should know what WebAssembly is: smaller runtime, binary, platform agnostic, running anywhere. I mean, these should be your points. You can even speak in the dreams. So it can actually do the slicing of the GPU attached to the whatever time the inferencing is happening, and then the GPU is being offloaded to another set of workloads that wants to do inferencing. Then dependencies and platform dependence. Yes, Python with a lot of dependencies cannot run on all the platforms, a single application. If you have to make it run with the GPUs, you actually have to test the application locally with the remote GPUs. But with WebAssembly, it provides you the development flexibility. So like Radu will be showing the demo how you can actually create the exact same scenario. You can write the code on your machine without testing it with the remote GPUs, and you can run it locally, and you can run it against the GPU which is there without even testing it. So it should work. Then the security, we know WebAssembly runs in a secure sandbox. So when you talk about the AI inferencing and you have your data that you want to have, private data, or it's not exposed or whatever that is, so you can be sure that it is secure. One of the another big points is the image sizes. So when you have PyTorch image sizes, so you can like anywhere from last I saw was 4 point some GB, so I just put that number over there. But yeah, it's pretty big images which are there, so you can imagine of pulling that image and then running it, whereas simple your application for WebAssembly will be a few megabytes in size, and also you can be closer to the data because it is able to run on any platform. There is a proposal in the WebAssembly for the machine learning called VASINN that aims to facilitate the machine learning inference for within the WebAssembly ecosystem using the same tools, same frameworks, so that the integration is pretty light. Like for example, the TensorFlow, Onyx, OpenVINO for seamless integration also aims to provide the hardware acceleration support, GPUs, GPUs to overcome the traditional WebAssembly performance limitations. We also saw one graph in one of the talks, how WASM with SIMD is more performant than the web GPUs, things like that. So those are some of the acceleration support which are there. Now we'll talk about Spin 2.0, what it is, what are some of the new features of Spin 2.0, and how we can actually create an application.
Thank you. So Saiyam mentioned Spin is an open source tool framework for building WebAssembly applications. It's fully open source. You go to github.com, Fermion Spin. You'll find it there with an permissively open source license. And the goal of Spin is really to help you create WebAssembly applications. It's primarily focused at building event-driven function-like services that run on the server side. And essentially, you build functions as WebAssembly components, and then you pretty much run them anywhere you can run a WebAssembly component. And if you've paid attention in the last couple of days, there's a lot of these places these days. Essentially, Spin has a bunch of language SDKs. Rust has obviously very good support for it because Rust and WebAssembly go very well together. But we also have really good support for JavaScript. You can write applications in Python and C# and a few other languages. Once you build your application, you write your application, you can distribute it using regular cloud-native tools to distribute applications. So if you use container registries, you can continue to use those, continue to sign your artifacts just like you use with any other artifact. And then you can deploy your application in a bunch of places. You can run it on a good old Linux system. You can deploy to cloud services like Fermion Cloud, or you can use some of the new Kubernetes integration that we just launched, and SpinCube and Fermion platform for Kubernetes. Over the last couple of months, we've been adding a bunch of features to Spin. So Spin, by default, comes built in with a way to do key value data. You can do relational data stores. You can do configuration, variables, and secrets. And one of the things that we're going to focus on today a little bit is you can do inferencing and generating embeddings directly from Spin and WebAssembly. And going back to what Simon was talking about for a second, the problem with AI inferencing today is most of services are using VMs or containers to package the logic for generating inferencing and distributing that using container images that get anywhere between 2-3 gigabytes to a lot more. You can easily see container images that try to do CUDA and PyTorch get to 7-8 gigabytes in size because you're obviously packaging a whole Linux file system, GPU drivers, PyTorch, and your application code. So those get very, very large. And so if we talk about trying to efficiently run those and scale to zero and start from scratch, and you get into a problem that you may be familiar with from the serverless world called cold starts, which means if you're trying to run that application on a new server, fetching 10 gigabytes is going to take a while. And then you'll have to find a GPU that you can take over and actually run an inferencing and then maybe be idle for the next 30 minutes and then do the whole cycle all over again. So is there a way that we can try to address this problem using WebAssembly? Well, what we've learned from WebAssembly for the last couple of days here at WASM.io is it's really small, it's portable, and it starts really, really fast. All of those are things that sound like things that we could address some of our problems. So what we've done with the language model implementation into Spin for inferencing is using WebAssembly and using component interfaces as the contract between the guest application and host components. We can assign essentially a fraction of a GPU for the duration of a request. Going back for a second to Spin, Spin primarily deals with web services. You build serverless APIs that get requests, they do some work, and then they go away. And then they might get a request again in like 20 minutes or even longer. So the idea there is to attach a fraction of a GPU just in time to handle a request, perform whatever work you're trying to do, and then go away. And that works really, really well for things like accessing a database or crunching some JSON and returning it. Historically, hasn't really worked that well for trying to attach to a GPU, or maybe wait for a GPU to become available, attach to it, initialize CUDA, initialize your PyTorch, and then do an inferencing request, and then go away again. So what usually happens is people keep those GPUs running all the time, attached to a single application, and it's essentially, yeah, that's while your application is running and waiting for requests, that GPU or that portion of a GPU is locked into that application. So using WebAssembly, what we can do is try to attach a fraction of a GPU to a request handled by a WebAssembly component just in time as the request comes in, execute your inferencing, and then shut down your WebAssembly component, use the portion of a GPU for something else. And so what that means is whenever a new request comes in, a request or a user at the other end of the request doesn't have to wait for a VM to start and then to attach a GPU and then to execute your request. And two, it also means that you can achieve significantly higher density and efficiency utilization for your infrastructure because you're no longer attaching, you no longer have a one-to-one mapping between an application and a GPU, and you can swap between them very easily. You can go from whatever utilization you currently have on GPUs to slightly higher because you have a multi-tenant-like environment. And so to achieve that, we have to solve two main problems. The first one is, if you've still paid attention over the last couple of days, you cannot really access a GPU from a WebAssembly module today. There are proposals in place. WASI GPU is one of them, Web GPU, and there are other proposals to do that very easily on the WASI side of things. But you need a way for your guest application, the one that needs to perform the inferencing, and the host that has a GPU attached to it to communicate to one another. And then once you do have that communication, how does your host actually execute the inferencing? And so spoiler alert, it's components. And essentially what we did for Spin 2.0 is we defined a WebAssembly interface. This is a part of a WIT file that comes with Spin. We have two functions for this. One is one that performs an inferencing, takes in the model, takes in a prompt, some parameters, and returns your result. And the other one is for generating sentence embeddings, and doing vector searches and things like that. And so this is by default coming by default with Spin and all the SDKs, and you can access that from any language that you can write a Spin application today. And once you build that application, you compile it to a WebAssembly component, and once it's a WebAssembly component, it'll have two imports that basically map to these two functions. And so once you have that component, you can run it anywhere you satisfy those two imports. And so you can run it around exactly the same component binary across CPU architectures, x86, ARM. You can run it across operating systems, and you can even run it across hardware acceleration devices. If you look at these two functions, they're explicitly not defining what kind of hardware acceleration they need to use. All they care about, they're high level enough that you don't specify, I need a CUDA GPU, or I need a TPU, or I need some multi-threading. It's left to the host implementation to define how to best achieve whatever result you're trying to get here without going into details, which is why you get portable guests, which means the component binary can run it everywhere, but the host implementation has to be specifically targeting whatever device, hardware acceleration device you may have available. So once you build that app, you can run it on your machine anywhere Spin runs, which at this point is pretty much anywhere from ARM machines to RISC machines to Windows, Linux, Mac OS. You can deploy to the Fermion Cloud, where we have A100 GPUs backed by Civo and Deep Green, or you can deploy them to the SpinCube and Fermion platform for Kubernetes, which was just announced this week. So let's have a look at what one of those applications can do and what they look like. So the entire source code for this you can find on github.com/Fermion. And let's have a look at a Spin application. Every Spin application comes with one configuration file that defines a little bit of metadata about the application and then a bunch of components. I mentioned that primarily we write web endpoints with Spin, but you can do any kind of event-driven programming with Spin. We have incoming support for MQTT if you want to do IoT workloads, support for queue-based events and things like that. There are a couple of key components that you have to define in your Spin manifest file. The one is, what is the WebAssembly component that I need to execute for this application? And then everything in Spin is following the capability-based model from WebAssembly and from WASI, and you have to define ahead of time the things that your component is allowed to do. And in this case, this component is not allowed to talk to any network host at all. It can use a key value store, which comes built in Spin, and then it can use the Llama 2 chat model. And we'll see in a second where that's coming from. And then this is a TypeScript application. I mentioned Spin has an SDK for TypeScript, which means you can write your application in JavaScript or TypeScript and then compile that together with a small WebAssembly runtime and generate a WASI Preview 2 component that can run anywhere we can run WASI HTTP, which at this point is WASM times serve and Nginx unit, and soon a lot more, including you can run it in Spin and then all the places I mentioned. So what this sample does is it takes a prompt, it takes essentially a comment, and then tries to decide whether it's positive or negative, a sentiment analysis, which is not really the best kind of example to show with a language model and inferencing, but we'll go with it for a second. If you're familiar with Llama 2, this is the regular Llama 2 prompt. And you're basically passing your user input, and then we have the analyze function that will eventually just call the infer function that I mentioned earlier. Eventually, there's an llm.infer call that happens right here. And that gets translated all the way to a WebAssembly import when you compile it to WebAssembly, and that's what it's going to execute. So in order to build this, you do a Spin build, which behind the scenes calls your tooling that generates a WebAssembly component. In this case, it's TypeScript, so it's npm run build, which does some stuff behind the scenes to generate a component. And then it generated the WebAssembly component that I mentioned in my source. It's 2.4 megabytes. And this WebAssembly component is able to do an inferencing request that will be satisfied by my host. So let's try and run it locally. And you can obviously have multiple components when building Spin applications. So let's try to do an awesome conference. And what is supposed to happen here is very quickly, this is supposed to tell me whether it's a positive, neutral, or negative sentiment. And it's taking a bit. And it's taking a bit because it's running locally. It's using, in this case, it's using Apple's Metal framework. But it's still a pretty big, like 7 billion parameter machine learning model. So it's take a while. But you can see in the corner, does a little bit of work, and then it's telling me that it's positive. So we just ran this using my machine, my processor, my M chip. Once you build it, I mentioned you can run it pretty much everywhere. And I mentioned Fermion Cloud as one of the places we can deploy the application. You don't have to deploy your entire application. You can just use the GPU from Fermion Cloud, which I mentioned is backed by Civo Cloud. There's an auth token that's going to go away in a second. But what this does is it tells Spin that whenever it encounters the infer function, instead of using the local GPU, it's going to pipe all the data through the internet all the way to a GPU, to an A100 running in the cloud, and then execute my inferencing and then give me my response. So if I pass that runtime config file and start my application again, I did not rebuild. It's actually the same WebAssembly component. This is, it's going to be hopefully somewhat faster. And it was, again, shockingly, using A100s to generate inferencing is way, way faster. So TLDR on all of this is once you build your WebAssembly component, you can decide whether you want to execute it on ARM or x86, back your inferencing with a CUDA GPU, or use CPU multi-threading, or some other currently uninvented hardware acceleration device. And so what we're trying to do is go from having to wait for an entire 10 gigabyte container to start, pull it from the internet, find a GPU, to you have a 2.4 megabyte WebAssembly component that tries to talk to a host that does already all of that for all the applications that you're going to deploy. And we've seen two places where you can run your application. Back to Saiyam to see how you can deploy this on SpinCube.
Yeah, so the next thing that we'll be doing is deploy the application on SpinCube. And we have a cluster already created. Radu is telling me to use K, but it's me who is not using it. So you can see I already have a Kubernetes cluster. This is a Civo Kubernetes Talos cluster, which comes pre-built with your Spin shim. And we have already installed the Spin cube. So you can see the Spin operator already here. So that we can run the Spin app, which is this. So you can see there is a Spin app. So since we have the operator installed on the Kubernetes that understand a Kubernetes object called Spin app, and in this particular thing, you can specify the spec, which is the image sentiment analysis. You can specify the executor. In this particular case, we are going to use containerd shim spin. And then you can specify the runtime config. Now here you can specify a bunch of things. For this particular case, it's the remote HTTP type and some of the options. And as mentioned by Radu, auth token will go away. So it's up to him. So you can see we don't have any pods as of now. And we'll just apply this. And we have the app Spin app created. So kubectl get Spin app pods deployment. Oh. Spin apps. And there's an app kubectl get pods svc and Spin apps. So it should give everything which is there. So you can see the pods which are there, and the service which is created, and your app. Yeah, the Spin app automatically translates it to the Kubernetes components that are required to run for the application. You can also do kubectl reverse proxy
Without CVG.
without
Yep.
this, and it should actually run
Localhost 9090.
localhost 9090, is it?
Yep.
9090. Yep.
And the
So
application's there.
that is running the same app on Kubernetes using SpinCube. That's it that we had for this particular demo. So we have shown all the three demos live.
And then resources, if you want to learn more about Spin, SpinCube, and Civo's carbon neutral GPUs, give those a try. Thank you.
Any questions?
Hi. Great talk. I have a question. So you were mentioning like hardware devices that are not yet existing, maybe. So I've seen there's FPGAs were mentioned on the slides. What would be the process in order to get those hooked up and that the data is like properly put to the device and goes back to the like Spin app?
Spin has an implementation, which if you go to github.com for me on Spin, you can see how the current implementation works for Apple's Metal implementation, CUDA, and just CPU inferencing. And essentially, it's a matter of having an implementation of an inferencing framework for the device you're targeting. TPUs is one that exists today that someone can implement if they wanted to. So it's a matter of finding an inferencing library that works on the device you're targeting, and it has the ability to execute your inferencing for the requested model that you want to implement it for.
Thank you for the talk. So in the component contract that you showed, I think I noticed that it looked like it was designed for language models. Is that what it's designed for, or is it general for any kind of model?
It was a high-level enough interface for now that it was specifically designed for language models. But back to what Saiyam was talking about with WASINN, that is a lower-level implementation that you can use to target vision, any kind of model that you want. And so, go ahead.
And following the previous question, let's say you have a cluster that has some NVIDIA GPUs and some AMD GPUs, whatever, and you get a request for some model that only has operations that are only implemented for NVIDIA, let's say. Yep. How do you find out, how do you query that, okay, where is that thing that decides this model can only run on this particular thing?
Yeah, quickly, and then if you want to, essentially, there's a matter of higher order or lower level the decisions that you have to make. The goal of the SDK is to let a developer get something done. Whereas application higher level configuration that targets the infrastructure, that's something that you might want to do at the scheduling or orchestration level as opposed to at the application level, right? And so if you've seen the Kubernetes manifest, Kubernetes is a workload orchestrator. In the Spin application manifest, you can specify the kind of node and the kind of infrastructure that your application requires. And that's something that you can easily do with SpinCube.
Thank you.
We're done with it? Okay. Well.